Hello dear students, the lecture today is about how random phenomenon is related with probability. And second, what are these interpretations of probability? The objective one of frequencies and the subjective probability. These are the highlights of an entire lecture that you can find on the description below. So let's start. Consider flipping a coin. If you flip a coin, you see, this is a random phenomenon if you don't know the outcome. So a random phenomenon is a phenomenon for which, like tossing a dice or tossing a coin, in which you don't know the outcome. So the outcome represents is this set, the set of outcomes, omega. Each point represents an event, an atomic event, a result of the random phenomenon. In the case of the coin, this is just 2 points, heads or tails. In the case of the dice, is numbers 1 through 6. So in general, you just have a set, you have many possible outcomes, atomic events, okay? And now, the probability function. The probability function assigns to each subset a number. A real number, you see, it assigns to sets, the probability assigns to sets numbers in there, but subjected to certain properties. First, it assigns to omega the number 1. So the first row is probability of omega is 1. More, probabilities are always positive. So for any subset A of omega, the number is also always positive. This is rule A. Rule B. More, the probability, consider this set, call it A. It must have a certain number assigned to it, call it P of A. This set has also a number assigned to it, call it P of B. So the third rule simply says that the number that you must assign now to the union of the two must be the sum, probability of A plus probability of B. Okay, so if A intersection with B is empty, meaning they are disjoint, like in the picture, then probability of A union with B is the sum of probability of A plus probability of B. Any probability law must obey these 3 properties. Okay? But how are we going to make the assignment? Because this is just properties. How are we going to do the assignment in practice? Let's see, there are 2 points of view. On one point of view, the objective one of frequencies, you will simply grab the coin, you see, you will toss this thing a billion times. You toss it a billion times, you have a billion results. And now you just count how many heads, you count how many tails, you divide by entire number of flips, meaning a billion, divide by n, and now you simply say, well, the probability of that I assign to h is this ratio, and the probability that I assign to tails, the atomic event tails, is this number. Okay, this is good, okay? Because, as a result, because these numbers are disjoint, probability of heads and tails is the probability of heads plus probability of tails. But look at the result. You see, this is nh plus divided by n plus nt divided by n, but this is nh plus nt divided by n, but this is just 1, because nh plus nt is 1. So you can see a definition like this will satisfy these properties. The same thing for a dice. If you toss a dice a billion times, you have n1, n2, n3 to n6. You calculate the ratio, and you assign the probabilities like this. Okay? So this is the first point of view, the frequencies point of view. It requires you to make this experiment. You run the experiment many times. You can do it on the computer if you have. If you know how, just flip a coin a billion times. The other point of view. Let's focus on the other point of view, the subjective point of view. The subjective point of view runs like this. You see, let's take the coin. You see, I don't know this coin, but I will make an assumption about this coin. The assumption I'm going to make is that it's balanced. If it's balanced, it means that when I flip it, the process will not benefit either heads or tails. As a result, I can say that the probability of heads is the same as the probability of tails. The same with the dice. I just say the dice is balanced, so as I flip it, the process doesn't benefit any of its sides, so each one of the 6 atomic events that can occur, numbers from 1 to 6, have the same probability. So this argument boils down to just add a new property, call it D, which says probability of atomic events is the same. Okay? Notice that I never flip the coin or the dice. I just assume this. I extend the rules to include this. But now this is a very interesting consequence. Let's look at it. For the case of the dice, for example, the probability for the dice, you have probability of omega is equal to 1. By the rule C, probability of omega is probability of 1 plus probability of 2 up to probability of 6. So this is rule number A, this is rule number C, and now, because we are under this assumption D, we can say something else. We can say, because, notice, probability of atomic events is the same, so this probability is the same as these, etc., is the same as these. So in fact, this is the same thing as probability of 1, 6 times probability of 1, or the 6 times probability of 2, etc., or 6 times probability of 6. Okay? But now look at what we have. Compare this with this. We conclude, you see, probability 6 times probability of 1 is the same as 1, thus probability of 1 must be 1/6, which is the same as probability of 2, which is the same as probability of 6. You see, you can do exactly the same thing with the coin. You see, probability of omega for the case of the coin is 1. You have probability of heads plus probability of tails, which is 2 times probability of heads, which is 2 times probability of tails, and thus probability of heads is 1/2, and probability of tails is the same as the probability of tails. You can see the argument again. It's very simple. Okay? This is very important. This formula is extremely important. Down here. Okay? Because now it allows you to compute the probability of all the other events, all the other subsets. You see, because if you know the probability of 1, 2 through 6, you know the probability of 1, 2, you know the probability of 1, 6, you know the probability of 1, 2, 3, etc. Why? Because the probability of these events is the sum of atomic events. Okay? This is very important. Because ultimately, what you have, if you have, for example, probability of a set A, and the set A is composed of, for example, A is the number, the outcome is even, for example. Probability A is even, and is an even number. Well, this is how many even numbers there are. It's 2, it's 4, or it's 6. But each one has a probability of 1/6. 1/6 plus 1/6, right? Using again C. But this is the same thing, just look at it. It's 3 times 6, but 3 is the size of A. So ultimately, this is the size of A divided by 6, but 6 is the size of omega. Okay? Once again, under the subjective interpretation, which has 4 rules, you just conclude this extremely important formula. Probability of A is the size of A divided by the size of omega. Okay? In other words, it's the number of events, atomic events, that favor the event A divided by the number of events or atomic events that exists in omega. Okay? This is a very important formula. And that's what you are going to use in many times, because the assumption that the atomic events have the same probability is a good assumption in many situations. Okay? Okay. This is all. I wish you a good work and see you next time. Goodbye.